Hi, it's Kate, and this is the second video for week 3 of Math 23b. So we've discussed what to do if a function doesn't have an elementary antiderivative. For most students of calculus, this was how integration was introduced when it was first introduced in their univariate calculus class. You take this interval from a to b, you divide it into n subintervals, and then you use some idea of maybe left hand, right hand, midpoint, trapezoid, depending on the function. One may fit better than the other as a means of approximating the area under the curve. And if it is an integrable function, the limit that you get when you take n, the number of subintervals, to infinity, is going to be the same as what you would get if you use the upper sum or the lower sum, which may just be more difficult to compute depending on the behavior of the function over the interval. Now, this is all fine and good, but our luck is about to run out. There are particular functions that are just really clunky to integrate using Cartesian coordinates, x and y. There are also functions that you're trying to integrate over a particular region where that region is really difficult to describe in terms of x and y. And so one of the things that we will have to do is choose a new coordinate system to use. And part of that process is reliant on the determinant. So before we get to that, we're going to talk about the determinant. We're going to see how it's quite powerful, and in fact next week is when we'll really be able to see what the determinant is used for, how we use it in integration. But for now, we're just going to be laying the foundation. So the punchline is coming next week. The rest of the joke is there, so to speak. We're going to talk about determinants for the remainder of this week's material, and then you're going to see how determinants take part in integration in other coordinate systems later. So the first thing is, reminder, we already talked quite a bit about the determinant of 3x3 matrices in the first half of this course in Math 23a. And recall that the determinant of a 3x3 matrix can be calculated as a function of its 3 columns. The first column crossed with the second, dotted with the third, will give you the value of the determinant in that case. Now, of course, when we get to higher dimensions, we're dealing now with n by n matrices. We can no longer take the first column, cross it with the second, and dot it with the third, but it is important to remember that the determinant still remains a function of the columns of the matrix. The defining properties are also still the same. First, it's multilinear. So if you fix n minus 1 of the columns in the matrix, the determinant is going to be a linear function of the vector that goes into that final column. It's antisymmetric, which means that if you swap any two columns, the determinant is going to change in sign, but maintain its magnitude. And normalization, the identity matrix, n by n identity matrix, the determinant of that is still going to be equal to 1. Now, of course, the difficulty with this type of definition is that you have to prove that such a function exists and that it's unique. So you have to give an algorithm of how to calculate it, and then you have to show that it's unique. I'm going to talk about a couple of algorithms of how to calculate them. We're going to go over them in class. We're going to show in class that these algorithms do preserve the 3 required properties of the determinant up here. And then in class, we're also going to show and demonstrate, we're going to prove uniqueness of this particular function. But I'm going to talk a little bit about how to calculate the determinant of an n by n matrix, and you'll get some more experience later in the week. The first way to calculate the determinant of an n by n matrix is something called development by the first column. It's also sometimes called expansion by minors in the literature, but it's usually how people prefer to calculate determinants. Let's take a look. We begin with an n by n matrix that looks something like this. And we zoom in on the values in this first column right here. Now we're going to take the number that's right up here, first column, first row, and we're going to use that as the coefficient on the matrix that results when we ignore the first column and the first row. So you take that entry and it becomes the coefficient on the remaining, which is now n minus 1 by n minus 1 matrix that you see right here once you've ignored the first column and the first row. Then we add on the next term. which is found by taking what exists in the first column, second row, right here, right underneath that guy, and that becomes the coefficient for the resulting matrix when you ignore the second row and the first column. So you want to take a look at what's up here as well as what's down here, what's left over there. And so this becomes the coefficient on the remaining n minus 1 by n minus 1 matrix, but we swap the sign. So it's multiplied by -1. We continue this pattern. We add on the next term. The next term is the coefficient on the determinant, the coefficient being the first column, third row. Then we ignore the third row, first column, and look at the determinant of the resulting n minus 1 matrix. And that's going to be positive. So it goes positive, negative, however many you have, all n. And what you're doing is always taking that first component that exists in the first column, that becomes the coefficient on the determinant of the remaining n minus 1 by n minus 1 matrix once you ignore that particular row in that particular column. That is development by the first column. Here's an easy example of it on a 3x3 matrix. I begin with first row, first column entry, that's going to be 2. I then ignore the first row and the first column. I'm left with this right here, that 2x2 matrix, and I'm going to take that 2 and multiply it by the determinant of that matrix, which happens to be 4. Then I'm going to subtract off doing the same thing with starting with the second row in the first column. Of course, that's a coefficient of 0, so it doesn't really matter what I'm multiplying it by, but recall that the way I would calculate this would be by ignoring the second row in the first column and taking a look at what's left over. Of course, what's left over would be a 1, 0, 0, 2 matrix, but of course I'm multiplying it by 0, so I'm going to say here 0 times the determinant of that, which would be 2. And then I want to add now, changing the sign again, going back to positive. First column, third row down here, that's going to be 1. And then the determinant of what's left over, once I ignore the third column, or pardon me, first column, third row, and what's left over is this up here, 1, 0, 2, 3. And that determinant is 3. When it's all said and done, what do we have? We have 8 minus 0 plus 3. So the determinant here is equal to 11. Another rule is to sum over permutations, and this is really unfun if you're doing anything higher than 3, honestly. So let's take a look at the 3x3 case, and you can see how it generalizes and quickly spins out of control for anything higher than that. You want to think to yourself, if I have the numbers 1, 2, and 3, how many different orders can I make out of those numbers? How many permutations? Exactly, that's where the name comes from. And so you want to write those out. Of course, that is n factorial different permutations. So in our particular case with the 3x3, that's going to be 6 different orders. I've written them all down here. And then you want to take a look at your matrix. Let's use the same matrix again. We have 2, 1, 0, 0, 2, 3, and 1, 0, 2. What you're going to do is you're going to create a term for each of these different orders. And here's how you create that term. With 1, 2, and 3, what you're going to do is you're going to take the first component, the first entry in the first row, the second entry in the second row, and the third entry in the third row, and multiply them together. So that's going to be 2 times 2 times 2. That's 8. Then you're going to determine whether it's going to be positive or negative by seeing how many swaps you need to do to this particular permutation to get it into cyclic increasing order. So it's already in increasing order. That's fantastic. So it's just 1, 2, 3. No big deal. There are no swaps, so we leave it as positive. Then we want to do the same thing for every single one of these orders. 1, 3, 2. That's the first entry in the first row, the third entry in the second row, and the second entry in the third row. So we have 2 times 3 times 0. That's going to be 0. Then we multiply it by, well, it's either positive or negative 1. We take negative 1 and we raise it to the number of swaps necessary to get these in cyclical order. Know that it would take 1 swap in order to get to 1, 2, 3. So that's going to be -1 to the first power. Of course, it ends up having no effect at all because it's being multiplied by 0, but you can see how you have to go through every single permutation, find the product of the corresponding components in each row, and then multiply it by -1 raised to the number of swaps necessary to get it in increasing order, get that permutation in increasing order. This is how we write that succinctly, right? We have a sum, and then in each term in the sum there's a product. There's the product of the various entries in the different rows of the matrix, multiplied by the signum function on the permutation function. So that is saying we take -1 and we raise it to the number of swaps necessary to get our permutation in increasing cyclic order. If you're still fuzzy on doing this out, a great way to see is whether if you've done it correctly is to try it, continue it on the rest of these to see if you end up with 11 again. We'll be doing another example of this in class, so not to worry if you're still a little fuzzy on how to do it, but you can absolutely tell already, especially if you get to even 4. I mean, 4 factorial, that's a lot of permutations to work through. Excellent exercise for something like homework to make sure that you have the right approach and the right understanding of the computation of a determinant. But if it's up to you and you can choose how to do this, I definitely prefer expansion by minors or development by the first column rather than summing over permutations. On the upside, at least we have a nice succinct formula that we can actually write down and understand.